Hello everyone, thanks for stopping in. Today we're going to be talking about Math 121, section 3.1. This deals with measures of center. So let's start off with a definition. What is a measure of center? And a measure of center is a value in the center or middle of a data set. It's a value in the middle of a data set, or in the center of a data set. A measure of center is something falling in the middle. We're going to talk about a few different ones. The first one we're going to talk about is the mean, which we sometimes call the arithmetic mean. And the mean is the value found by adding all data values together and dividing by the size of the data set. And dividing by the size. It's the average. Most people like to think of the mean as the average, right? It's the value found by adding all data values together and dividing by the size. It has three important properties. First is samples tend to have similar means when taken from the same population. Samples tend to have similar means when taken from the same population. This means if you have a population you want to study and you collect 10 different samples, you should expect each of those 10 samples to have fairly similar means. Another property is the mean incorporates all data values. All data values. And the third one is the mean is not resistant. Not resistant. Now, what does resistant mean in statistical terms? Well, that's our next definition. The next definition is resistant, which is whether or not outliers have a strong effect. So the resistant is, a data is said to be resistant when outliers don't have much of an effect on it. A value is resistant if the presence of outliers does not affect it too much. That's what resistant means. It's resistant if a value is not affected too much by an outlier. So the mean. Let's think about a data set. You have a data set and you calculate the average. Now, make one of the numbers 1,000,000 times bigger. The average is going to become quite a bit bigger because of that, right? An outlier, a number that's 1,000,000 times bigger than all the other numbers, will have a big effect on the average. So resistant is when outliers don't affect it. The formula for calculating the mean, well, the mean has two symbols. The first, we're going to say mu equals this weird symbol, which is called sigma, of x over capital N, or, and we'll talk about what these mean in just a moment, x bar equals that same weird sigma symbol, x over little n. All this is saying is telling you to add up all the data. So let's define these terms. Mu, this weird looking U letter. It's called mu. It looks like a U with an extra vertical line on the left side. This is population mean. Population mean. And big N is population size. Now the reason we have different symbols is because x bar is a sample mean. It's called x bar because it has a bar over it. And little n is the sample size. So population mean and sample mean, they have different letters. Make sure you're aware of that. If you're talking about a population, you're going to use the Greek letter mu, which looks like this weird U. It's pronounced mu. Mu. If you're using a sample, you'll use x with a bar over it, called x bar. And similarly, big N for population, little n for sample. This is the size. N is the number of people in the population, the number of people in the sample. We use big for population, little for sample, because populations are bigger than samples, right? Samples are subgroups of our populations. Now, X is data values. It's just a placeholder for the data values, and sigma is the symbol to sum. It means to sum. If you've ever used Microsoft Excel, you might have seen this symbol before because this is the button that adds up all the numbers. That's what it means. It's pronounced sigma. So, the mu, the population mean, is equal to the sum of the data over the size. That's exactly what the average is, right? We just have it written out formulaically now. We have a formula. The sum of the data over the sample size gives me the sample mean. The sum of the data over the population sign gives me a population mean. The only difference is which symbols you use. You use the Greek mu and the capital N for population. You use the English x bar and the lowercase n for samples. Now, let's have a hint. A hint is that Greek notation is generally for population. In general, when you see Greek letters, you should assume they're for a population. Now, let's take a look at our first problem here, calculating the mean. Heliod has been studying solar flare occurrences for each year for the last 10 years. His data is shown below. What is the mean number of solar flares for a year? Notice, has he collected a population or a sample? It's a sample, right? So my sample mean will be equal to 7 plus 9 plus 11 plus 11 plus 12 plus 14 plus 16 plus 17 plus 20 plus 21 over, and now we divide by the size. It told us there should be 10, but we should always double check just to be sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll divide by 10. Now, we need to add things up. 7 plus 9 plus 11 plus 11 plus 12 plus 14 plus 16 plus 17 plus 20 plus 21 gives me 138 over 10, which will give me a final answer of x bar equals, divided by 10, 13.8 solar flares. Now, can I have 0.8 of a solar flare? No, but that does not mean the mean, the average, cannot be a decimal. Be careful with that. We'll talk about specific rules for rounding in a moment, but for now, we'll just say we want to round to 1 decimal place for this value. Now, we have a caution here, and the caution says the word average can be misleading. We should say mean. We should try and get in the habit of using the word mean when we're talking about an average. The word average can be misleading. We should use mean. Sorry, I forgot the word use here. We should use the word mean. We should use the mean instead of the word average. Now, the median is the data value that's actually in the middle. This one isn't necessarily as formulaic, it's in the middle. So the median is the data value in the center of the sorted data. It's the one smack dab in the center, smack dab in the middle. The properties of the median, it's resistant, is resistant. Outliers don't change it very much. If I know what number's in the middle, that number will still be in the middle even if the biggest number becomes 100 times bigger. It doesn't change the position it's sitting in. The median is resistant. And the median does not use every data value. does not use every data value. The median doesn't use every data value. It's just the number in the center, right? There's not a formula we're punching all the numbers into. So it doesn't use every data value. Next, let's talk about calculating the median. There's a couple steps. The first step is sort the data. If the data's already sorted, awesome. If it's not, we got to sort it. Step 2, cross off endpoints until left with 1 or 2 values. Step 3, find the mean of the 2 values if necessary. Find the mean of 2 values. If you get 1, you're done. If you get 2, you need to find the mean of them. So let's take a look at this. We want to sort the data and cross off endpoints is the strategy. So let's take a look. We've got 7, 9, 11, 11, 12, 14, 16, 17. Looks like they're in order. So I've already sorted my data. So if I want to find the median, I just need to cross off endpoints. Well, I'll cross off the 2 on the end. Then I'll do it again. Then I'll do it again. Then I'll do it again. And now I'll stop. I've got 2 left in the middle, right? I've got 2 here. Well, I got to find the number halfway between them. So the median will be the average or the mean of those 2. I use the term MED, med, for median. Some people use the whole word median. It's up to you if you want to abbreviate. But that'll give us 26 over 2, which gives us 13 solar flares for our answer. So when we did the median, we got 2 numbers left in the center, and we had to average them. We had to find their mean to get the answer. Now let's look at the next example. Assume now that Heliod recorded data for another year and found that there were 17 solar flares for that year. So I have a new data set. I have all of the original data, 12, 14, 16, 17, but I'm going to put an extra 17 in because the question tells me to do that. 20, 21. And now I'll do the same thing. I'll cross off endpoints. I've crossed off endpoints twice, thrice, 4 times. I'm left with 3. Do it again. I'm left with 1. 14 is my answer. So this time, the median is just the number 14. Notice, sometimes you're left with 1, sometimes you're left with 2. And that is the median. The median is interesting because sometimes it's actually a better measure of center than the mean. The reason for that is outliers. If you ever have an outlier, the median will be better than the mean, generally speaking, because the median is not affected by those outliers, but the mean is. So be wary of outliers. Outliers lead you to use the median more frequently than the mean. The next one is mode. Mode is the value or values that occurs most frequently. It's which number shows up the most in your data set. It has 2 properties. The first is a data set can have 1, none, or more than 1. We're going to write our 1s. More than 1 mode. You can have 1, none, or more than 1 mode. You could have 1 mode, you could have 2 modes, 3 modes, 17 modes, or no mode. And we'll see what that looks like, how that happens in a moment. Number 2, the mode can be found for categorical data, for qualitative data. Can be found for qualitative data. The mode can be used with qualitative data, which is nifty. You can have categories. For example, What's the most common eye color? Brown eyes are the most common because that's the most dominant allele in the genotypes, right? So brown eyes are the mode for eye color. It's not the average eye color. I didn't add up all the eye colors and divide by how many people there were. I found the mode, right? So let's find the mode. Find the mode of the original solar data set. Let's see, 7, 9, 11 appears twice. 12, 14, let's see. 11 appears the most. So the mode is 11 solar flares because it appeared the most. It appeared the most frequently. Now, let's talk about finding the mode. Finding the mode is step 1. Determine which value or values are or is, which value is repeated the most. If there is a tie for first, those data points are all modes. If you have a tie for first, let's say you have 3 numbers that all appear 7 times, then all of them would be modes. You can have 3 modes. If they tie, then you can have multiple modes. The second part is if no values are repeated. There is no mode. If every number in the data set only shows up once, there is no mode. Like if your data set is 1, 7, 9, 11, 56, 29, 107, I didn't repeat any numbers there. There would be no mode in that data set. So be careful. There might not be a mode. If nothing's repeated, there is no mode. The mode is usually the easiest one to find. It's because you're just asking yourself which number showed up the most. Which data point showed up the most? I keep saying the word number for data points. They might not be numbers, right? If it's the mode, you could be looking at hair color, eye color, birth city. You can be looking at categories as well. Our last value is the mid-range. And the mid-range is the value halfway between the minimum and maximum. Data values. It's the value halfway between the minimum and the maximum data values. The formula for mid-range is mid-range equals max plus min over 2. A pretty easy formula, right? You take the biggest number, you add the smallest number, and you divide by 2. Properties. The first property is it's not resistant, which should be obvious. If you're only using the max and the min, if you have an outlier, it's going to be the biggest or the smallest. It's definitely going to affect your data, right? Your mid-range. So it's not resistant. And the second is easy to compute. That's a big advantage of the mid-range. It's easy to compute. You just need to know 2 numbers, the max and the min. You don't need to work very much with it. So let's take a look at finding a mid-range. Let's see, we've got a data set here, and it says to find the mid-range. So I'll write mid-range equals, what's my maximum value? Looks like 21. Plus, what's my minimum number? Looks like 7. It's easy when they're sorted, right? Over 2 will give me 28 over 2, which is 14 solar flares, is the mid-range. 14 solar flares is the mid-range. 21 plus 7 over 2 gives me 14 solar flares. Now, I said we would talk about rounding rules, and rounding rules, there's one rule we need to follow. We round our measures of center to 1 greater decimal place than the original data. We round our measures of center to one greater decimal place than the original data. If the original data is all whole numbers, your measures of center will have one decimal place. If your original data has numbers that have 2 decimal places in it, your measures of center will have 3 decimal places. It's always one more. So you identify how many decimal places your data was measured to. Let's say it's, your data goes to 7 decimal places. Then your calculations will round to 8 decimal places. Always one greater decimal place. You always go one extra decimal place. So that is why on the first page we rounded to, or in the first example, we rounded to 13.8 and kept it. Because our original data was whole numbers. One more decimal place than whole numbers is 1 decimal place, right? So we'll always be rounding to one more decimal place than the original data. Make sure you're rounding correctly. Always one more than the original data. Now, we have one last formula and one last idea, and that is the so-called weighted means. Now, weighted means are values that have a bit of a weight. So let's write the formula and then define it. X bar, it's a mean, right, equals the sum of, and now here I'm going to do f times x over the sum of the f's. Now, this might seem weird at first, but let's define what the symbols mean. X bar is still the mean, right? Sum still means to sum. What are f and x? F